So now let us see the delta modulation system. So noise in DM system. Okay. So in this case also, there are two types of noise components. One is a quantization noise, and other one is channel noise. Okay. So we talk about first quantization noise. In delta modulation system, we know this is signal is transmitted in the form of single coded pulses. Single coded pulses means either plus delta or minus delta. Okay, that means either 0 or 1 in terms of bits. Otherwise, in terms of voltage levels, it is either plus delta or minus delta. So in delta modulation, the signal is transmitted as plus or minus delta. Okay, isn't it? Then the difference, then the maximum difference, that is the maximum error called quantization error, is equal to how much, or how it is changing? It is changing from minus delta to plus delta. Okay. So then what about its probability density function? If we take probability density function, okay, probability density function, how much is this? Here we assume it is again equiprobable. If it is equiprobable, by using simple diagram, you can find it out. So it is the quantization error component, and this quantization error component is changing from minus delta to plus delta. Okay, isn't it? With the constant probability density function. So let us say this constant value k, and from this we can calculate area of or area under this probability density function k into 2 del, because minus del to plus del, the quantization error is changing. So that's why the area under this one is equal to 1. Now k equal to 1 by 2 delta. All these things, all these things are already we discussed with respect to PCM. Okay. So therefore, so quantization error probability density function in case of DM system or DM signal is equal to how much? 1 by 2 delta. So once you know the probability density function and also its range, we can evaluate its mean square value. So mean square value is obtained by integrating between minus delta to plus delta of error component square into its probability density function Fe of EQ into EQ. Okay. Now we know its value. We know the probability density function of this one. So it is equal to minus delta plus delta EQ square 1 by 2 delta dEQ. Okay. So now what is the value here? 1 by 2 delta. It is Q cubed by 3 into 2 times. Okay. It is just a minute. Value is simply equal to how much? It is del square 2 to cancel, and it is del square by 3. Okay. Now we find out, and this is the error due to the quantization process in delta modulation system. And this error is distributed over a frequency range of how much? Frequency range of sampling rate. Okay. So this entire mean square value is distributed over the frequency range fs. So then we can write its corresponding noise power spectral density, okay, Gn q of f equal to the total mean square value del square divided by 3 fs into 2 times, because it is two-sided spectrum. Okay, that's why 2 into, okay, I'm writing it as L square 3, okay, to 1 by 2 fs. Fs is the frequency range over which this entire mean square value is distributed. And when we're talking about partial density in terms of two-sided spectrum, we need to divide it by 2. Okay, we need to divide it by 2. That's why we have this factor 2. Okay. So now we can write this as del square by 6 fs. Okay. So this is a noise, quantization noise power spectral density as far as a DM signal or DM system is concerned. Okay. Now we need to find out its corresponding noise power, quantization noise power, that is P N Q is obtained by integrating over the band of message signal. So let us say the message signal frequency range is from 0 to fx. Fx is the maximum frequency. Fx or W. Okay. So if you take it as W, you can take, if it is fx. And if you are talking about a two-sided spectrum, you can take it as minus fx to plus fx. Noise power spectral density Gn q of f into df. So it is 2 times of 0 to fx. Value is del square by 6 fs into df, and it is simply equal to how much? 1 by 3. So we get 1 by 3, and after integration it is also del square, and how much is this? It is simply becomes, it is fx, okay, divided by, just I'm writing. So after writing this, what about fs? Fs is also constant. We have integrated with respect to fs only, sorry, f only, and it is equal to fx. Okay, so it is simply equal to del square by 3 into f. Now let us say, calculate the signal power. Signal. Okay. So how much is the signal power? How we calculate? Let us assume the signal S of t is a sinusoidal A into cos 2 pi fxt. Okay. Then what about the power then? Signal power is simply written as a square by 2. Okay, because it's a sinusoid. So we can easily calculate that. Okay. Now, in delta modulation system, there are normally 2 errors will occur. One is slope overload error, an important error. Other one is granular error, but the most important one is slope overload error. So according to a formula, we can reduce the slope overload error. What is the condition for that? Okay. The condition for that is, okay, A into, that is slope of this one, A into 2 pi fx should be equal to slope of the delta modulated signal. Okay, Ts. Okay. Now, what about amplitude? Amplitude should be del by Ts into 1 by 2 pi fx. Okay. And this should be equal to del by 2 pi into fs. 1 by Ts is nothing but equal to fs by fx. Okay, we can write like this. Okay. So now we can substitute here this Ps. How much is Ps? Signal power. It is del square. Okay. A square by 2. A square by 2. Del square by 4. 4 into 2 means 8. It is 8. This is fs by fx. Now we have signal power and noise power, isn't it? Now we can calculate output SNR as output SNR corresponding to quantization. That's why I can write it as only important compared to the channel noise. That's why I'm writing it SNR Q equal to signal power by quantization noise power. So how much is signal power here? It is del square by 8 pi square fs by fx whole square. Quantized noise. How much is quantized noise? It is calculated as del square by 3. Okay. So I'm writing it as del square by 3 into how much? Fx. I think fx by fs. So it is fx by fs. So it is simply equal to del square cancel, and it is equal to 3 by 8 pi square. Okay. And into, and you see these two will be multiplied, so it will be raising by a factor 3. So fs by fx whole cube. So you see, this is an important formula you need to remember. You need to remember it is equal to, therefore output quantization, signal to quantization noise ratio equal to P by 8 pi square into fs by fx whole square. This is an important issue. Okay. So now based on this, you can easily compare these two systems. Okay. So if you want to compare PCM system and a delta modulated system, there are 3 factors. So one is bandwidth, okay, and second one signal to noise ratio, and third one hardware complexity. Okay, complexity. Now regarding bandwidth, what about the bandwidth of PCM? We take PCM. Okay. Just a drawing, these two. So bandwidth of PCM equal to how much? We already determined in the third unit itself. It is equal to n. What do you mean n? N is the number of bits used to represent each and every quantization. Fx is the highest frequency. And fx or nw, depending upon the choice which you use. Okay. So fx or w is the highest frequency of a message signal, isn't it? And in case of delta modulation, so how delta modulation is a special case of or 1 bit PCM. So then what about its bandwidth now? Bandwidth of delta DM system, delta modulated system is equal to n equal to 1. It is simply equal to fx. So you see, when you compare nfx and fx, nfx means n times of fx, which is the bandwidth required in case of PCM, whereas fx, bandwidth of message signal, is the bandwidth of delta modulation system, okay, which is only exactly same as the bandwidth of message signal. Okay. So in these two cases, PCM requires more bandwidth than the delta modulated system, isn't it? The second one, SNR. Okay. Regarding SNR, what do you say? SNR of we are talking about here maximum SNR. Okay, maximum. So maximum SNR is equal to, in case of PCM, equal to 2 power 2n. Okay, in case of PCM, the maximum SNR is equal to 2 power 2n. Okay, whereas in this case, DM case, in case of DM, SNR quantization, okay, DM equal to how much? Just now we determined. How much is that? This one. Okay, so 3 by 8 pi square into fs by fx whole cube. Okay. Here it is straightforward to evaluate the SNR, but it is indirectly you need to find out. So here fs means sampling frequency. In case of, I mean, when you are comparing SNRs of PCM and delta modulation systems, you know, the other factors like bandwidth has to be constant, has to be the same, isn't it? So when bandwidths are same in case of PCM and delta modulation system, okay, what about sampling rate? Sampling rate, bandwidths are same. Okay, bandwidths are same means it is how much is the bandwidth? N, fx is the bandwidth, and here it is fx. And when you write in terms of sampling rate, it is 2, sorry, it is n. If you multiply numerator and denominator, it is simply becomes 2 times fx. It is 2fx by 2. Okay. So what is this actually? This is n fs. It is simply equal to fs by. Because I'm writing this is f dash. F dash means sampling rate in DM. Okay. So therefore, sampling rate in DM is equal to n times the sampling rate in PCM. Okay. So when you compare, when you want to compare delta modulation system and a PCM system based on signal to noise ratio, you must assume that bandwidths are equal. At what condition the bandwidths are equal means if the sampling rate of DM system is n times the sampling rate of PCM system, the bandwidths are said to be equal. So under this condition, what is the SNR of DM system? SNR of DM equal to 3 by 8 pi square into the fs dash. Fs dash here equal to n times into fs by fx, and you can also write this nfs means 2 times n into fx. So I can write this as 2. Okay, I'm going to write other way. So here I'm going to write it is 2 times n fx also. So here it is actually 2 times n fx by fx whole cube. So it is equal to 3 by 8 pi square into what happens answer. It is simply equal to 8 n cube. Okay, and 8 will get cancelled, giving 3 times. Okay, 3 by, I'm sorry, pi square is also there. So it is equal to, pi square is approximately equal to 10. So it is 0.3 n cube. Okay, so you see, when we compare here, this one with the 2 power n. So in case of PCM, it is SNR PCM equal to how much? 2 power 2n, whereas SNR DM equal to 0.3 n cube. Okay, now we can compare. So which one is larger, which one is smaller here? These two, we can easily compare. Okay, by taking, if you take n equal to say some 8, what about SNR of PCM? It is 2 power 16. Okay, then what about SNR of DM? It is equal to Achari? Achari?
Sir.
Okay. So SNR in DM system is equal to how much? 0.3 into n cubed means n is here how much? 8 cube. So how we can write this 0.3 into I can write this as 2 power 3. Okay, 2 power 9 totally. So 2 power 9. So now we can compare these two. Okay, because both are in powers of 2, except this small factor, 0.3. You can compare these two. Okay, so which one is larger? PCM is larger. Okay, so for PCM system, signal to quantization noise, signal to total noise as well as the quantization noise is more compared to SNR of DM system. Okay, so this is how we can compare both the systems regarding SNR. And regarding complexity, PCM is more complex than DM system. Okay, PCM is more complex than DM system. Okay, why means in case of PCM we need a equipment, we need hardware to convert a analog into digital, and also at the receiver we need to have hardware to convert a digital into analog. Whereas in DM system, both are actually integrated into a single chip, which is normally called codecs. Okay? So why means in a DM system, a part of a modulator itself will act as a demodulator. Okay, we know this. So that's why DM system is having less hardware complexity compared to PCM. So as an overall, when you compare these two, as far as the bandwidth is concerned, PCM is having more bandwidth than DM system, and also as far as the signal to noise ratio is concerned, PCM is having more signal to noise ratio compared to DM system. But as far as the hardware complexities is concerned, DM system is less complex compared to PCM system. This is about the comparison between DM and PCM systems. I think with this, the noise performance of all communication systems are over. Okay. Hello? Hello?
Sir,
Okay. Any queries?
no, sir.
So